So, Aperture-based daylight modelling with something in French as a subtitle. Before we get into this, it's just something to think about. Take a look at those and just think about those during the presentation in the dull moments. Okay, so this is a story that began on a very long journey, which was the long in time, that is. Well, actually quite a bit of hopping around Europe as well, various meetings. So I sat on this European standardisation panel for what seemed an eternity, from I think 2011 to 2018. So this was the Daylight in Buildings standard. It was approved in 2018, and indeed it superseded British Standard 8206. This year it was adopted by the UK. Now I focused on the daylight part, but what I saw was all the sort of problems and confounding factors there were with the sunlight parts. This is how this whole story of aperture-based daylight modelling, it began with just sitting there and seeing all this sort of sunlight stuff that was appearing in the standard and thinking there must be a better way of doing this. And there's a whole raft of less than ideal methodologies which are used to account for sunlight in planning and guidelines. So they look at certain times of the day or year. They either ignore the direction of the sun or will count it until a certain angle and then say it doesn't count anymore. Yeah, a dead angle. Right? So by not accounting for the angle, that means that until that dead angle, that sunlight beam counts the same whether it's facing normal or coming in grazing. Yeah, it counts as an hour, say, or whatever. Yeah. Crucially, none of them, at least none I could see, made any account for the size of the window. They ignore or cannot account adequately for shadowing effects of frame bars and window reveals. And again, they either ignore or cannot adequately account for shadowing caused by surrounding structures of buildings. So yes, you'll have crude approximations in terms of angles and so forth, but unless you actually go down a simulation route, and most of these methodologies are really sort of 2D or kind of 2.5D, you're going to have very crude measures. A lot of the stuff that's out there, certainly in BR 209, you'll see it always described in terms of idealized geometry in built forms so that you can handle them using the Waldron diagrams, which are still much beloved in certain professions. And you can't come up with any meaningful aggregate measure for a whole dwelling. Very limited information on the temporal dynamics. Yeah. You're just considering sun exposure maybe, for certain times of the year. The annual probable sunlight hours, again, there are issues with that. We'll look at that a bit more closely later on. Key thing is these things are all conceived in a sort of pre-digital age. So even in the latest European standard, you'll see things in terms of 2D plans. Indeed, that's from the standard. So there you're meant to do all of this and then, okay, that counts. No, it doesn't. It's beyond the dead angle and so forth. Those approaches don't really work in a world that looks like this. Yeah. So what ended up in the standard was pretty much a dog's breakfast. Yeah. Because it was a conflation of all of these suboptimal approaches. And it was only sort of sitting there every 6 months or whatever when there was a meeting and just thinking there has to be a better way. And indeed, well actually this is dog's breakfast number 1. I should say there's another one later on, we'll see. And what it required really was actually just starting off with a clean sheet completely. Just looking at this absolutely in a fundamental way, more like actually a physicist would, if you will, because they need that. That is my background. And actually, it's incredibly simple. Once you get rid of all the baggage, the idea almost just appeared on its own. So the sunlight beam index is that. An area measure of the connectedness of a building aperture to all of the possibly occurring sun positions for that locale, for where the aperture is placed, yeah? And for that particular aspect of aperture, including all possible obstructing surfaces. So whether it's a big building, or a nearby reveal, or a brise soleil, or a railing from a balcony, or an overhang, anything. And it's averaged across the aperture surface. So if the sun miraculously stood still for 1 hour, normal to 1 meter square of aperture, you would get 1 meter squared hours of cross-sectional area of sunlight beam that would pass through the aperture. Incredibly simple. Yeah. So look at that graphically. There's the beam that can go through when it's normal. And as it moves away from normal, you'll get reduction in 2 ways. You're getting less of a cross-sectional area because of the cosine effect of the projection, but then also you're getting, wherever you've got any reveal of any sort on the outside, you will get shadowing caused by that as well. So the sunlight beam index is simply this for all of the possibly occurring sun positions for the whole year. Okay, so it's a simple line of sight calculation for a grid of points at the aperture to the sun position, and then just repeated many, many times for all possible sun positions. And actually, given the nature of this talk, please, if people want to interrupt during it, then ask a question, please do, because there'll be quite a few ideas in this, and you may just want to actually answer those have those questions addressed sooner rather than later. Okay, so the actual method I use to generate a grid is called a sort of stencil method, where you create a radiance image of the aperture, and then from that you extract the sensor grid of points. So it means you can cope with any shape of aperture, no limitation on that, and you can create that grid as fine or as coarse as you want. Okay. So what does it look like in practice? So 1 meter square set in a thin wall, and then the same square meter set in a 20 centimeter deep reveal. Okay, so this now we'll place this in London and look at the sunlight beam index, the annual value for the main compass and the mid-cardinal directions. So the cumulative annual sunlight beam index, 1 meter square vertical in London. And then if we look at south, that's kind of our marker, if you will. So in the thin wall, we're getting nearly 2,000 meter squared hours cross-sectional area of the sunlight beam that can pass through the aperture. Yeah? So whenever the sun is above the horizon and in front of that plane, some sunlight beam will pass through the aperture. But with a 20 centimeter deep reveal, drops down by about a third, just from the shading of that deep reveal. Okay, now if we see how it changes with 45-degree increments. Not much when you're going southeast, southwest, but then quite a drop from 45 degrees further on, and a dramatic drop going from west to northwest and east to northeast. Notice even when you're facing north, you get a little bit, because in those early morning in the summer you'll get a little bit in the morning and a little bit in the evening. Okay. So a single bottom line number that tells you about that aperture's connectedness to the sun. But you've done a temporal calculation, so you actually have all of that information as well, if you want it. So the way to read this is this is all the hours of the year organised in terms of 365 days and 24 hours. So this thin line going along here would be sort of January the 1st, January the 2nd, and so forth. So what you're seeing now is the sunlight beam index actually at a 15-minute intervals, which is why it's quite fine here. So the highest values, of course, for south-facing is in winter around here, when the sun is at its lowest and midday. And actually, as you move here towards sort of midday in summer, it's quite a bit less because, of course, the sun is much higher up, so you get less of a cross-sectional area of beam going through there. As you increment this by 45 degrees, the total amount doesn't change too much, but what you see now is this penetration happening more in the afternoon, of course, because it's facing to the west here, and you're starting to see this start to sort of join up. And if you went further to the west, you'd see a big yellow blob here, yeah, where you're getting low-angle sun in the afternoon entering the place. Okay, so that's just for a 1 meter square aperture. You can add all these up for any arbitrary collection of apertures. So this work was actually funded by Velux, which might explain the presence of roof lights there. So the initial idea for the sunlight beam index did get some support from Velux, but otherwise this is purely sort of endogenous research, just done for its own sake. So all of these are in groups here. There's a sunroom there. So same process, just do this for every aperture, and then you can just add everything up together. So for a particular location, a particular orientation, I actually can't remember which one it is, you now have a bottom line number for the whole year, but a map. And indeed, rather than seeing that very fine-grained detail, it might be easy to digest if you divide this up into sort of AM and PM monthly totals. Okay. But what we've got now is a value for the whole dwelling, so that's nearly 18,000 meter squared hours. So this is the connectedness of all of those building apertures to all of the occurring sun positions. You've got 25.5 square meters of glazing. So if you were to divide that by that, you end up with something which is kind of an efficiency parameter. It's how efficient is all of that glazing at bringing sunlight potentially into that space. And you might want that number to be high or low depending where it is in the world, whether it's in Scandinavia or say further south in Spain and so forth. But where it gets really powerful on a sort of planning, for planning purposes, is when you start to look at possibilities. So the same dwelling, this is for London, but now with our 8 different orientations. And you see dramatic changes in both the bottom line annual number, but also the distribution, AM and PM and monthly. So there you can see with that orientation, you know, the dwelling's getting really everything in the morning and very little afterwards in PM. Look around here. So this is the highest value, 24,500, but actually it's quite evenly distributed. You look at this one here, this is much lower annually, but this might be the ones where you're most concerned about summertime overheating, because high irradiation in summer afternoons is a much stronger indicator of overheating risk than if that was in the morning or other times of the year. So you've got something which visually is very compelling, but also very informative. Any questions or even comments on this before we go on to the next part? Yes?
Is the sunlight beam index prioritised to be at a higher value when it's sort of instant?
Yeah, when you've got the greatest beam that can pass through. Yes, yeah.
I wonder the relevance to that inside a room, like where maybe people would appreciate sunlight being incident on surfaces or different types of angles. Because just look at it, surprised me. I hadn't thought about it. First thing you showed where in winter it's higher. Obviously, it makes sense because that's where it's. But in some ways, it sort of seems counterintuitive just because it's sunnier in the summer. And I wonder if there's some sort of middle ground which might be relevant to how people experience it inside the room. I'm not sure, but yeah.
We may actually, I won't try and answer that now because I think what you see towards the end may go some way to addressing that.
Sure.
So there was another one here, was it? Yeah.
Yeah, you may be coming on to this, but the question is around trying to maximise winter gains and minimise summer gains in a UK climate, naturally ventilated building. Does that emerge out of the data?
You're thinking this now in sort of building performance terms, aren't you, rather than sort of planning? I think if we get to that towards the end, yeah. Sorry, I think Graham was next.
Is there any difference according to what sort of glazing it is?
No, we're not looking at the glazing at all. It's just at the aperture, so we're just in front of the glazing.
How about different colours for review?
Sorry,
different colours, because you've shown a lot of windows with white, done white. They could be other colours.
Oh no, we don't have any transmission properties yet or anything. We're just looking at the aperture's potential for sunlight. This is looking at very much in terms of basic planning. Yeah, we're just looking at the built form, just the geometry. Sorry, yeah.
I have the same question.
Oh, okay, fine. Okay, so we'll go on. So this is the sunlight. Sorry, all right, one more.
The unit is meter square average, so it doesn't take into account the solar radiation on glazing angle, or is it normal?
Oh no, it's including for the angle. It includes.
No, but that is only for the foreshortened area of the aperture, not for the solar irradiation, because this meter square average, so it doesn't have any irradiance. The quantity doesn't have any irradiance.
Not yet. No. No, it's purely geometrical. It's a.
The sun is perpendicular, or.
Oh, it includes for the angle. Yeah.
Well, just for the shortened area, not for the actual intensity of the.
No, it doesn't look at intensity. It's purely in terms. So imagine that there's no glazing in the building. It's just for that aperture's potential. Yeah.
Sorry, quick one. I hope you have answered to later on, but what about the urban context where you have that?
Oh yeah, you can have whatever you want. Yeah, in fact, there is some context to this one here. There's a few houses around, and there's a perimeter that cuts off very low angle sun to account for, further on sort of urban context. And you can have whatever you want, any geometrical concept. You'll see examples of that.
So the calculation is based on a typical meteorological year?
No. It's just purely location. Actually, it's interesting this because everyone's approaching this from a building performance perspective and not from a basement. Just think in terms of just geometry at the moment. Okay, just the geometry. Okay, so it needed a companion. I thought, okay, we've got the sunlight part, and actually the skylight part is easier still because the sky doesn't move. So this was incredibly easy. So the aperture skylight index, again, it's an area measure of the connectedness of an aperture in terms of the illumination received from a uniform luminant sky dome averaged across the aperture. Okay. So a small detour now, if we go on to that. Why not the CIA overcast sky? Because if you look at the most influential documents that we have, like BR209, it's an overcast sky. Any reason why we shouldn't have an overcast sky?
Sun. Yes, sun sometimes.
For example, for daylight-based the climate modeling, you have to use the sun.
Oh, we're just looking at just the connectedness of an aperture to the sky.
Right, because actually we get blue sky, for example, and it's for the north sky.
Exactly. So it's not always cloudy. In fact, it's not that it's not always cloudy. The actual CIA overcast sky pattern is actually a very rare occurrence of overcast skies. Majority of overcast skies do not have a pattern that conforms this, and we'll see this in some measurements. Yeah. It's not just they don't match it exactly, they deviate markedly from this. And I was hoping Paul would be here to back this up, yes. So a quote from a paper by Paul Littlefair, a colleague, that it's an extreme type of overcast sky. So that was in 1995, and we became aware of this because in 92, BRE installed a sky scanner, was it 91? And we'll see a little bit of that in a moment. So, does it make sense to base any sort of a standard on an extreme case without good reason? And no good reason has been given. The daylight factor was conceived as a way of kind of rating an interior independently of the actually occurring conditions. And actually, as an idea, that's fine. Stephen.
If I may add, also, it's the lowest brightness of the range of sky. So if you're working to maximise deliver a light level as a percentage, then it makes sense to use the least bright sky.
Well,
I'm not trying to defend the daylight factor, don't worry.
Well, no, because you don't. When you say the least bright sky, it's not necessarily the least bright sky. It's the distribution you get for what might be one of the least bright ones. But it is extreme, and we'll see this. This is building 9 at the BRE, which I think sadly is no longer with us. Got knocked down a while ago. On top of building 9, there was the experiments for the International Daylight Measurement Programme, which the BRE were part of, and so they had this sky scanner on the top, and they had shed load of the best equipment available at the time, and importantly they measured as well as the sky brightness pattern, but also they had measurements of the 4 vertical illuminances, as well as horizontal. That did happen earlier. Oh, okay, that's back, fine. Okay, where are we? Oh yes, just go back here. Now, just below this room, they had a pair of, below this roof, they had a pair of office spaces, 9 meters deep, which they monitored. A set of 6 photocells. This was actually part of a completely separate measurement program that was about innovative glazing. So they cycled on one room various advanced glazings, prismatics and so forth. And then this one was just kept clear glazing. And I've actually kind of started my career on this data set because I said, actually, if you put these two together, you've got the perfect set to validate a lighting simulation program, which a number of us were just starting to use around that time, which was called Radiance, of course, which has since taken over the world. So this ended up becoming pretty much the sort of benchmark validation of Radiance and showed it capable of enormous accuracy if driven correctly. Okay, but there's the measurement pattern of the sky scanner. Yeah.
Given the fact that, assuming that most of the openings will be windows, using a uniform sky as the geometry will actually have more illuminance reaching than actually an overcast.
Let's see that in a moment. Yes. So this is the CIE standard overcast sky pattern. There's the zenith, and there's the horizon, and there's the zenith. And this is a visualization of an actual measured overcast sky. They're nearly all very lumpy. Very rarely do they get to that. So this is from the skies that I got, the 750 odd skies from the BRE. This is a slice of brightness going from south to north across the zenith, just an arc. And it's for all the skies that fulfill this condition where it was above 1 kilolux global horizontal, less than 25, and there was the difference between global and diffuse was less than 1%. So in other words, there was insignificant direct normal here. So most of those skies will actually be quite a bit lower. But when you draw that arc, for those skies, there's the CIE sky. This is the average of all of those. And the thing is, these are all over the place. And if you do a daylight factor calculation based on the difference between global horizontal, diffuse horizontal and internal, you end up with a whole range of values around the actual CIE overcast sky precise one, which is in red. In fact, you nearly end up with you always end up with an over prediction. That's the average of all of the actually occurring ratios. It's only if you have access to the 4 vertical illuminance values and that the coefficient of variation between those 4 is very low, less than 5%, do you actually get close to guaranteeing that your skies conform to the CIE overcast sky. So in other words, the short version is that real overcast skies are predominantly not like the CIE overcast. They don't have this high ratio of 3:1 of the zenith to the horizon. And given that the daylight factor is about ratios, it's not about absolute values and whatever, this idea that the CIE overcast sky, which was adopted in 55, somehow makes the worst case condition doesn't really stand up, because the rationale has never actually been made. And I go so far as to actually say that, which is probably considered a heresy in parts, but I really do think that was a blunder, and it would have been much better to just stick with a uniform sky for daylight factor calculations, and importantly, for vertical sky factors, like we'll see. Okay, so yeah, there we go. Hopefully it's not going to do that too often. So end of the detour, back to this. Okay, so we're going to use a uniform sky for this. Now we have to give this uniform sky something. The sunlight beam index kind of came with its own numbers. Here you have to give it some numbers. So I thought, okay, why don't we start off with a uniform sky that gives 2,000 lux on the horizontal. That way, each square meter of horizontal glass that can see the whole sky therefore gets 2,000 lumens. Why 2,000? Well, those numbers are comparable with what you're getting in the sunlight beam index. But it also means that for a vertical aperture, oh no. David, do you want to phone him up? There's that number I think in the cupboard, he said.
Right.
Yeah.
It's not a timer on your...
No. No. So what that means is that you end up with 1,000 for a vertical aperture. Yeah, 1 meter square. So 1 meter square vertical aperture gets 1,000 lumens maximum. So if it's in a thin wall, you get the 1,000 lumens. If it's in that 20 centimeter deep reveal, see, that drops right down to 690. Yeah, so just the shading from that reveal is enough to block off enough of that skylight. Add an overhang, add something else. Yeah, and you end up with this single number which tells you about that aperture's connectedness to the sky. And it's not being biased by any particular sky brightness pattern, because there is no good reason to do so. Okay, so we can look back to our house model, do the same thing. There's the actual context that it had, and that was just to account for sort of general low density built up area. And we can end up, here we go with this. So the green is the aperture skylight index. So this is the connectedness of all those apertures to the sky. You end up with this bottom line number of 17,700 lumens of connectedness to the sky. The sunroom only is just below there. That's 5,000. So there are 5,000 of those are accounted for by the sunroom. And I just put in 3 orientations for the house, so you can see the huge change in the sunlight beam index, but also the sunroom only part. So easy to isolate features of the building and see what their contribution is. So here, even though you're getting quite a bit less in the house overall, you're getting a bit more in the sunroom. Pardon me. And of course, you can look at the temporal dynamics of this and find out when it's happening. Any questions about this skylight part now? David.
John, I'd like to come back to your statement about the blunder at some juncture, because the implications of that are mind-blowing, as peanuts would say.
Well, the implications of what we found out in that 1955 paper that showed that actually Waldrom's assertion right at the very beginning was wrong is quite mind-blowing as well.
Except there's an awful lot of people out there trying to do that. Some of the work we've been doing has actually come up with some completely crazy results. So one of the things we have actually questioned is, what about this thing called the CIBSE Sky? Now you're actually saying it's a load of nonsense, but
well, if we're basing a standard, it doesn't matter so much in climate-based daylight modelling, of course, because using absolute values and the sun contributions so important. And
so your statement about being a blunder needs some degree of qualification.
It's if you're basing everything on it, if your outcomes depend on it, as we'll see in a moment when we do the comparison with BR209. Okay, so we've got that part. So onward, but actually no, there was something else in there, and that was, it actually came about from, again, sitting on the EU standardisation, because there was two dog's breakfasts in there. The first one was the sunlight part, because that was really messy. Anyone think what the other dog's breakfast was? Dog's breakfast number 2. Actually, that's dog's breakfast number 3, probably. Yeah.
What about the reflection from the walls?
Well, no, we're not doing any of that yet. No.
You got that far,
Yeah. It's view. View's really confounding because it's so difficult trying to account for views. Like, oh, am I seeing here? If I move along here, it's a bit there, so move over there. And so you have all of this stuff in there, and it just unwieldy. Absolutely unwieldy. And then there was that rare moment of ping, light bulb going on, so rare that it allows a cheesy transition. Really slowed down so you can appreciate there, and indeed twice. And it was this. Yeah, just to think of it like this, instead of actually thinking, okay, we're getting, well, C. So, each square metre is 2,000 lumens of connectedness to the sky, like that. Okay. In a thin wall. Now we face horizontal. So now that's gone down to 1,000 lumens. It's behaving itself now. So I think only if it really fails badly should we tell you this. So, okay. Where have those other 1,000 gone? Well, if you make the ground glow, and you say, well, that's it, you're getting 1,000 lumens of connectedness or view of the ground. Yeah, you've got the same view of the ground as you do of the sky. It's half of your hemispherical view of that, from the aperture there. And then what happens if you've got an obstruction in there? You'll have less than 1,000, plus whatever lumens of connectedness that you're getting for that obstruction. So in BS 8206, which has actually now just been superseded, but you've got the same sort of rationale in there, they talk about view layers. Yeah. Upper distant view being the sky and its boundary with the natural or man-made seam. Yeah, the middle layer, man-made objects, natural or natural ones, and then the lower ones. So we can extend this aperture skylight index idea, in fact actually even forget about even calling it aperture skylight index, and just think of it in terms of 3 layers of connectedness from the aperture to the external environment in terms of the connectedness to the sky, the connectedness to the ground, and connectedness to the obstructions. Okay, so it's only once you've got that potential at the aperture can you then actually start to think about what's happening inside. You know, that determines what happens inside. And in terms of a basis for planning, this simplifies things enormously. I mean, I don't say what those numbers should be, it's about having a methodology for determining them. Okay. So firstly, given that this is such an off-the-wall idea, you know, does it make any sense? Because ultrasound, there wasn't anything remotely like this. So it's like, how do you begin to determine if an idea this off the wall makes any sense? So, okay, let's again do it really simply. Let's look at just look at illumination arriving at a point from one polygon. Okay, so we've got one polygon, 1 by 1, and we'll look at the illumination arriving at a point spread out along this line, the y-axis, and we'll look at 3 view vectors, one directly towards the polygon along that line, one at 90 degrees and one at 45 degrees. Okay, so now I first showed this work actually just a few months ago at the Radiance workshop, which was in New York this time. I was a little bit apprehensive about showing this at the Radiance workshop. So that's why. So in 2004, we're doing stuff like the New York Times, full climate-based modelling, glare analysis. I can't remember exactly how many polygons, but it was in the hundreds of thousands. And so there's all this cool stuff. And then 15 years later, you show colleagues this, one polygon, 1 point. And for those of you familiar with it, this is like reception infants radiance class, you know, first morning commands like that. You can't get any simpler with radiance. So we'll look at the view. Actually, it's the hemispherical view that's important, not the angular one, because the hemispherical one relates to the illumination effect received at that point. So that's when you're just 0.2 units away from that 1 by 1 square. Okay, so if we look at that, so the number there now is the illumination effect of that green obstruction. Okay, so when you're looking directly at it, it's nearly the whole hemisphere, so it's going to be close to 1,000. Yeah, but it's 921. If you're looking at askance at it, 45 degrees, goes down to just under 700, and at right angles, 300. So quite a big change. So there's the distance in those units. So this is the solid angle of that polygon, which of course doesn't change irrespective because the distance doesn't change. Doesn't matter where you're looking, that solid angle stays the same.
John, do you think you could just go back a few slides to show the position in 3 dimensions?
Sure, yeah.
So it's the spot nearest.
That's the nearest one there.
Right,
yeah. Let me just scoot forwards. Okay. So now we'll look at this as we go further back. So there we were 0.2 away. So at 0.5, get an illumination effect. At 1. Two and 5. Okay, so visually, kind of, well, yeah, looks like it might make sense. Actually, if you plot those values, so here's the distance. Again, this is on a logarithmic scale, and here's the illumination also on a logarithmic scale. So just look at the 3 black lines first. So that was the highest value when we're right close to it. Okay, so that 1,000 is the value at the top there, so we just below it, 921. And that's how it falls off with distance. When you're looking at 45 degrees, you've got quite a bit less, you're at 600 or so, and there it is, dropping off dramatically. And when you're looking at 90 degrees, of course, you start off just 300 now, again, drops off very sharply. Now, this is showing, again, logarithmic scale, the solid angle subtended by the obstruction. It follows a very similar rate of change. Okay. So now let's look at this a little bit more complicated, a few more polygons now. So the reveal depth's a bit larger here, just to sort of exaggerate the effect of shading. So when we're illuminating this with our 2,000 lumens from the outside, now it doesn't matter where they are, it can be ground, ground or sky, or any combination of the two, or indeed obstructions. This is what that distribution looks like because of the reveal. Even at the center, of course, you're getting a maximum value which is quite a bit less than the 2,000, which you would get in a thin wall. And the minimum in the corners, 471, and the average is 1,100. So the average is quite a bit less than the 2,000 or the thin wall. Now this is quite a deep reveal. So we'll look at this effect now. First thin, then with the reveal, and for these different obstructions. And we've made the obstructions and the ground luminous. Why is the sky red, not blue? Well, we've simply just done it top down in sort of graphic terminology, RGB, so yeah. But at least the green's sort of in the middle. Okay, so if we've got a thin wall and just take one point in the middle, it's going to be exactly the same as our aperture. We're seeing 1,000 lumens. Well, 1,000 lux here, sorry, this is always lux, whereas this is actually lumens because it's averaged across it, yeah. So it's a little bit different here. So we're getting 1,000 lux there and 1,000 lumens across the aperture because it's thin. And we're seeing just as much ground as we are sky. As soon as we put our reveal there, you see, okay, that point in the middle, we're getting less, for sure, but this is actually what we're getting across the whole aperture. Okay, now we put an obstruction there. So even though that from the middle, of course, it looks like it's in the middle of the field of view, so it shouldn't matter. If you actually were moved to view this from the corners, you'd actually see bits of this cut off. So the luminance effect of the obstruction from the middle is different when you account for it over the whole aperture. And for those obstructions, again the values, and for that one there. Even for that one, it look a little bit different when you view it from the corners. You get a bit clipped off. Okay, so you've actually now got something which can give you an objective basis for some measure of, of view, and it's quite a robust measure. This is a way you're actually making view a material quantity in considerations. It's never been considered as material previously. It's always something that's been too qualitative. Sorry. Yeah.
Just one question. View, as I understand, it's mostly related to just a solid angle. I don't quite understand the reason that.
Well, this is the view potential from the aperture.
Yeah, I understand, but to me, view is mostly related geometry to solid angle.
And that's the way it's always been treated, for sure.
Yeah, but what I don't understand how it is being tied up with illumination and light level.
Right?
Because you might have some light level there, but your view is, the solid angle is quite big, but based on the cloudiness or the...
Well, you saw that earlier. I mean, there, you see this solid angle is much larger, which that's 400, and this is 136.
Oh, sorry, that's the light level, the left color.
Sorry, the green one there, that's the, solid angle part, yeah. So it's accounting for the larger solid angle, but it's doing it in terms of illuminance effect.
So what's the reason that we should tie the view to light level?
The reason is in this one here, in this slide back here. The reason is there. You see, that solid angle is the same. But when that object is way off over there, you can hardly see it. Because it's from the aperture's perspective. If the aperture doesn't get it, you're not going to get it inside the room.
Solid angle change. If you were talking about the solid angle of the green object.
No. For that object, when that object is over there, its solid angle hasn't changed.
No, of course it would change because you would subtend a different angle.
No. Now what's happened is the viewpoint, the view direction has changed, but the point hasn't changed. The distance hasn't changed.
Yeah, that's good.
Yeah.
But no, if only that wouldn't just, if only it moved around the radius. But if it moves in a horizontal way, of course.
Yeah. Well, but it does. I mean, this is. You have to unthink a lot of things, I think, for this. And certainly, anyone who's interested, I can send you the paper that was presented at Building Simulation. That caused a lot of knitted brows, I think. Kind of stopped people in their tracks a bit, that one. Okay, just to go on, where are we? Where were we? Okay, it's back. Fine. Okay, so where are we now? Okay. So, sunlight beam index and connectedness of the aperture to the view layers. You put those things together, and that's where the title of this talk came from. I think it does warrant its own little moniker, I think, for this, because it is a completely different way of looking at something. Actually, the surprising thing is it's so incredibly simple, and yet it came nearly 25 years after climate-based daylight modelling. Requires maybe a pause for thought there. Yeah. And it certainly caused people to sort of stop in their tracks at the Building Simulation Conference because it was so incredibly simple. Has anyone been like building simulation? It's just full of ever more conflated modelling practices with increasingly fuzzy boundaries and Here you've got something that is, you can't gameplay. If you've got good geometry, you will get a correct result, because it's purely geometrical. And having sat on a panel where you try and formulate standards and so forth, so they can't be accidentally or deliberately gameplayed. Okay, so now we'll do a comparison with BR209. Is anybody from the building research establishment here? You are? Oh, jolly good. Okay, somebody you can take up that corner. Are you familiar with BR209? Jolly good. Right. Because I've never actually used it in practice. Now, Andy Bissell, who we're hoping will be here, has used BR209 lots and stuff, and he's aware of the aperture-based and thought, oh yes, I can see that, and so forth. So, okay. So differences between the annual probable sunlight hours. Okay. So now, way I understand it with annual probable sunlight hours is as long as the sun is shining onto that surface, it counts as a 1. Yeah, it's a hit. Doesn't matter whether it's face on or at an angle. Yeah. And then what happens is you apply a probability of hours. You say, well, you know, whatever percentage of hours in that year for that locale. So that's something that will be distilled from climate data and so forth. And you'll say, okay, you've got so many of those above horizon hours for the sun will be sunny. Yeah. Okay. So key difference is it doesn't make any account for the angle, which of course the aperture sunlight beam index does. So right, what I've shown comparison with is sun hours. So that's where the sun is above the horizon and it's shining on the surface, it counts as a 1. But there's no measure, of course, of the actual size of the aperture or surface which it's hitting. Yeah, that's not a consideration in the BRE guidelines. So the way to think of it is, if the maximum here would be when the sun was actually normal onto the surface, then you would see all of that the same colour, if you will, because it all counts as a 1, and you add all that up and that would give you your basis for annual probable sunlight hours. Okay, so I just took an example from here, just as a starting case. So yeah, I just did a crude modelling of something like this. I actually put a dividing wall there as well because I didn't want to model the whole thing. It's more than enough to see it on a couple of apertures. So there it is. We've got something with a sort of deep there, essentially it's like a very deep reveal, if you will, for this, because we've got a balcony and overhang and sides there. We've got 2 floor to ceiling, well, yeah, more or less floor to ceiling glazing there. Doors, so that's got a total area, I think, about 8.26 square meters. Okay, and a little rail there. And we'll show results for just the thin glaze, just the glazing on its own. So in other words, no context, no reduction caused by structures there. And first look at the skylight connectedness. Okay, so the first thing, BR209 uses the vertical sky component, and that's using the CIE overcast sky. So that means its maximum is just under 40. With using the uniform sky, of course it's, well, if I cranked up the AD number in, it'd be very close to 50. Radiance uses a Monte Carlo simulation, so it's never going to be exact, but often very close. This is a shade of a percent off the theoretical value of 50%. Okay, so you have very different numbers to start off with. But again, the key thing is you've got a measure because it relates directly to the area. So you've got 8,234 lumens of skylight connectedness. You put your building context there, and now, of course, you've got the distribution, you've calculated at every point there for a grid. So you have your area weighted value of 27.5%. There's the individual ones. Of course, that one's more to the center, so it's higher than that one there. And of course, it's much lower here because you began with much less, because the illumination effect is concentrated towards the zenith, the CI overcast sky. And you got your 4,552 lumens of skylight connectedness now. So you've lost nearly half of that by the structure around. So we're just looking at the skylight connectedness now. Okay, the sunlight part. So the window's facing south. Okay, ignore the colour here, and the scales are all very different because there's no variation when it's just the window panels themselves with no surroundings. Windows facing south. There's the key thing there. So you got that. You're getting that irrespective of the size of those windows. Yes, that's just the number that you get if you count a positive 1 for every time the sun hits that face. This now is showing 15,922. Sorry, Stephen, yeah?
Average sun hours for London.
Sorry, no, average, that's the average across those two surfaces. Sorry, ignore, yeah. It's not for London, yeah. Sorry, by London in terms of its geographical position. There is no climate in this, so there's no variability, yeah. Yeah, so it's not, this is the basis under annual probables, unlike ours. That's just a factor, yeah. That's not the important thing. The important thing is there you've got this measure. You'd have nearly 16,000 metre squared hours of cross-section area of sunlight that could pass through those windows in the absence of anything else. As soon as you put something, oh, and of course you've got your temporal dimension there. As soon as you put that something else around it, it changes quite dramatically. Okay, so this goes down now to 8,600. Now, here I'm showing the average value for these panes. That's not what you would do in BR209. In BR209, you would take I think it's at 1.6 meters above, I think, something like that. So you would select a point there. So essentially you would base your calculation on point values 1.6 meters above there. And yeah, depending on the exact nature of the shading, that might get you in the ballpark of the average value. Yeah. And of course, you've got the temporal dimension there as well, showing exactly where those losses are happening. You're getting a big drop in the summer penetration because, of course, it's south-facing with a deep essential overhang from the balcony above. Okay, now look at the windows facing west. Okay, again, ignore these colours. It's just these numbers now have changed. And there's the temporal distribution. But the key thing there, when we put some context there, so we can see again how this changes, but again, west facing, so we're getting quite a bit here in the late afternoon, early evening, and so forth. So, to sum up the differences between BR209 and aperture-based daylight modelling. So, first and foremost, it's one of basic conception. I mean, BR209 was conceived at a time when the calculations would have been carried out like that, and of course they did a very good job, you know, within those limitations. ABDM was conceived in an inherently 3D world. You're looking at a spray of calculation points, a grid across each aperture. Yeah. So, I mean, the key thing there is the word aperture. You're looking at the effect for the whole aperture. You're not selecting points. And for the skylight part, again, difference is we're using a uniform sky. We're not biasing to an extreme type of sky, which rarely occurs, and include the size of the window. Now, we know from planning officers that they're sort of intuitively doing this. In fact, at the meeting we had a couple of years ago, do you remember the one on planning and so forth, where one of the planners in London said, actually, there are times where we'll go and see, well, strictly speaking, it doesn't match the VSC criteria, but it's such a large window that it doesn't matter. So this is now just giving an objective basis for something that's kind of seems to be happening at an intuitive level. Anyhow, come on. Right, here we go. So that was the skylight part. So the sunlight part, again, similar thing. You know, this is happening at a point. We're doing it across the whole aperture, and we're accounting for the size of the aperture. And you're getting a complete temporal evaluation. Now, how you choose any basis afterwards, that's up to you. You can look at, should it be a certain amount in each month or whatever. Yeah, it's about having a methodology which can really cope with anything. And then when it comes to view, well, again, I think it's just dealt with qualitatively, however much it's mentioned in BR209. With the aperture-based, you've got some potential there to make some objective measure of the impact of obstructions. Another key difference, and it'd be interesting to hear from any practitioners on this, is that certainly, for the ones I spoke to, is to say when they carry out an evaluation on site layout and planning using the BR methodology, that happens, it gets written up, but then that's the end of it. That model is never looked at again. Just gets parked. Then they go on to the, I think this is the projector overheating or something. Whereas with here, you just, aperture-based light modeling, you can start off with an incredibly crude envelope model, and then as you refine your apertures and adding more detail, you're carrying on adding and refining. And then you can use those models later on in subsequent modeling, in other modeling paradigms, as we'll see. So you can start to have a much more efficient and smooth workflow. Apparently he didn't actually say that. It was Roger Sessions, a composer, who was paraphrasing for him. But I think aperture-based light modeling is incredibly simple. I think it's as simple as it can be. I don't think you can make it any simpler. Where next with this? So the first thing here is that there's a continuum between these. How do I calculate aperture-based modeling metrics? I actually use my CBDM software. I just use in a slightly different way because they're all calculated using the same daylight coefficient matrices. You're just treating them in a different way, and actually a much simpler way because you're only looking at the direct component each time, whether it's for sunlight or skylight. Because there's a continuum there, what you could of course do, and I think this is what many people were alluding to earlier, you can climatize aperture-based light modeling. You can start off with this framework, and as you want to refine your modeling, you start to climatize it. And that can mean using standardized climate files, putting the sensor grid just behind the window instead of just in front, so account for its transmission properties, and so forth. However which way you want to do it. Whatever level of complexity, you don't throw your models away, you just keep building on them and adding whatever complexity you need to. And if you want to apply climate data, sure, and then you can start doing, if you want, go down the full route of interreflection and so forth. So this really should be thought of as almost a subset of climate-based daylight modeling. But it's a very simple one, and in fact you don't need radiance to do it. I use radiance, but in principle you could just have some sort of widget that plugs in a Revit or Rhino or whatever and just goes and does a line of sight calculation for a grid of sensor points across the aperture. Hopefully somebody will make such a widget. Climatization of aperture-based measures, actually it's already happened, and it happened in this project, which actually started off in 2005. So this building will be completed next year. It's been some time in coming. The legal agreement for its development includes an aperture measure of daylight injury predicted using climate-based light modeling. So we weren't going into the space. So the space was the adjacent Art Student League building on West 57th Street. So this is a visualization of what it's going to look like when it's finished. It's still covered in scaffolding, at least it was a few months ago. So in this historic building here, 1875, every great American artist has been associated with it in one way. So on the top you have the rooflit studios. Okay, I can only find some really old photos from that. Now, the artists, of course, highly value these spaces. When the adjacent lot was sold to developers and an outline proposal appeared in 2005, they were concerned about the loss of light. So they were offered daylight factor. They didn't buy into that. They were offered shadow patterns. They thought, that didn't really make much sense. And remarkably, because not many people knew of these techniques at that time, but the people who were advising the users of the building knew about my stuff, and asked, could we use climate-based? And I said, well, yes, it's like putting a light sensor on the window. Well, actually putting an array of light sensors across the windows of the Skylight, adding up the hourly values throughout the whole year, getting your total annual light using, and you're simulating it using New York data, of course, sunlight and Skylight, and you're reflecting off the buildings. And then you do the same thing with the tower in place. And look at a tower that's completely black and obstructing, and one with a 50% reflectance. So this was the original simulations done back in 2005. There's the key thing, an area-weighted measure of the total annual illumination on those apertures. Existing, black tower, proposed reflectance 50%. It's in tabular form, so you could halve that loss with some reflectivity. So this was an aperture-based measure. Back then, a long time before anyone thought of calling things aperture-based. And it figured in the legal agreement for the development. So when the final proposal came about, which wasn't until 2013, the long time was of course caused by the crash in 2008, which put sort of mega projects like this on hold. It had to be re-evaluated to show that it wasn't significantly worse than what had already been agreed, which turned out to be the case. Another thing here, ABDM. A means to encourage mindful modelling. Mindfulness, a word we hear a lot of nowadays. Maybe we should think about it in modelling terms as well. Why? Well, back when radiance came out, and indeed quite a lot of the CBDM approaches, they were based on the Unix toolbox model. That's just one line of script for that has about 5 radiance commands in it doing various things. Now, of course, a lot of people saw things like that. Well, that was their reaction, so they stayed well away. And it was only people that really sort of got stuck into radiance back then in the early 90s that learned how to do this that became the experts in lighting simulation, especially daylight simulation. Those were hard-won skills. I think anybody that sort of mastered radiance, I know there's a few in the room here, will tell you it's not something you pick up overnight. Now it's very easy to use advanced simulation. This is actually one of the less intricate things. This is and I don't use these tools. I got this from Eleanor here, so you can ask her any questions if you want about this. This is actually for parametric geometrical modelling, isn't it? But a similar sort of thing with environmental modelling. This is a Grasshopper thing. Grasshopper is a scripting tool, a visual scripting tool. It's not the actual tools that run off and do the simulation. It's a way of putting them together and getting them to do stuff. And people have made these techniques incredibly user-friendly. So you work in a purely graphical way, and you're just joining stuff up to do all these complex simulations. Now, what practitioners will tell you, possibly first once they've looked over their shoulders both ways, is it's now so easy to do. They're getting concerned about whether or not the people using it, including some of their own staff, actually really know what's going on under the hood. Now, when daylight simulation was difficult, you kind of had to know what was going on because you had no choice. It was a mindful way of doing things. Now that it's got incredibly easy, and not just in the practitioner world, I've seen in the academic world, you've got people doing stuff and they have no idea what's going on under the hood, but the output looks great. It looks stunning, and even their supervisors might think, oh, that's good. Yes, they're producing lots of fantastic stuff here. Now, with code, you can work through this. You can find out what's happening at every stage. The number of times at especially academic conferences, people put up things like this as if it means anything. It means absolutely nothing except for the person who did it. Even then, they're probably not sure. For most of us, it's just grasshopper spaghetti. Yeah. So, is there anybody here who's French? Who can speak French? say it then, because your accent will be better, the first bit. Yeah, much better than me. And it means?
Go back in order to jump better.
Yeah, one step back and able to launch yourself forwards better. Yeah. So I think if we start to look at, and really understand what's happening at the aperture-based level, then we'll be much better prepared to find out what's going on inside those spaces. So if we know our aperture-based measures, our sunlight connectedness, our skylight connectedness, and so forth, then we can start to think, well, what might this, daylit luminous interior be like? So I've got those measures. Actually, maybe those apertures should be larger. So even before you start doing any detailing, start to get some idea of those measures. I think once we've done a bit of this, we can start to think, well, actually, given that we've got this happening with those apertures, and let's say that's it, we're not going to change those apertures, we can say, well, maybe we can start to say things about that interior space. Just how deep should it be? How should it be partitioned up? Instead, we're going straight into those spaces and doing a lot of complex modelling, which is now incredibly easy to do, and we have to start wondering, are we actually producing reliable results here? What's the potential for views out? We can start to climatise these aperture-based measures. Because you've got a location for your building already. Hopefully, you know where it's going to be. Each aperture will therefore have a particular orientation. You'll know its sunlight connectedness. So then you can start to apply climate data to that to look at the overheating risk. Of course, with that climate data, you've got the air temperature as well. So even without doing thermal modelling, you may come, I'm sure you can come up with some very good proxy values to show you about the potential for overheating risk. And this is from something that's largely geometrical with the application of a little bit of climate data. So do that first, understand what's going on before you get into all the noodly modelling stuff. Immediately you'll get some idea. Do we need solar control? Do we need electrochromic glazing? Is there sufficient sun exposure to warrant all of those things? So, should this idea go forward? Someone already asked me, is this going to replace BR209? I don't know, there's someone. Well, I'm not going to put you on the spot there, but just by show of hands, does anyone think this idea has the potential to replace BR209? Okay, does anyone think it doesn't have the potential? So that means there's people undecided. It's a pity, because if someone put their hands up and said it doesn't, I was going to say, okay, why doesn't?
You bring the standards into the equation as well, so that because industry at the moment is catching up.
What I say. Once you've got something like this, you have to rethink. I mean, the very fact that the standards don't include the size of the window. That's a big step forwards. As soon as you actually have something that counts for the size of the window, then it's like, okay, we have to completely rethink stuff. But we've got a basis now where we can start to come up with things. Now, we know there's, you can charge a higher rent when you've got better views and so forth in a building. So I think you've got the scope to actually make some direct connections between sort of, say, rental values and positions in buildings, especially where you've got like-for-like apartments and so forth. At the moment, people are attempting to do things to find out how much people value their space, and they're doing simulation studies and all this, but they're dealing with factors that are so woolly and go through several stages of woolly modelling. I think the results are never reliable. Here you've got something that's entirely geometrical, and I think once you start off with that very objective, like hyper-objective basis, I think then you've got some chance of relating people's subjective appreciation of those measures and how they relate to them.
That's a good question. You sat on the panel, didn't you, over European standards discussions? Yeah. Was not this brought up then?
Sorry?
Wasn't this brought up then?
No. This came afterwards. No, this was from sitting there, and I just sat on. I had more than enough on my plate with the daylight part and stuff. When seeing the sunlight part and just seeing them mixed together all of these ideas which were never great to begin with because they all came from this 2D plan world and they've tried to shoehorn them into 3D digital world. Yeah, so these ideas only happened because I sat and saw that. If I hadn't sat on that panel, these incredibly simple ideas would never have occurred to me, possibly no one. David.
John, what work have you done with architects to test this out? Because I was always taught that the natural light inside the room was a function of the size of the hole in the wall.
It's not a bad start. Sadly, you rarely get to work with architects because the process is very fragmented. Right. Ideally, these things should happen at the very earliest stages of massing, for sure. But a place where this can have real value is actually in teaching architects, because it gives you an almost tactile, tangible feel for things when you talk about them in these simple geometric terms. Yeah, I mean there are architects who are absolute whizzes at doing complex simulation with Grasshopper and all these things, but that's almost like charging ahead. They haven't done that step back because they haven't had the chance yet. I mean, I would see huge value in this, like, year one architecture, so people start to learn exactly what this aperture's potential is. Because only then, that dictates everything that's going to happen inside the spaces anyway.
Strong agreement with you, but why is we're only discovering this now? I mean, is it something to do with the fact we've had glazing systems that are effective?
Why? Who's going to this? Okay, Velux, very great. They funded a bit of the development for the sunlight beam index. Yeah, but that was a small amount compared to what you get in a grant funding. I think my chances if I went to a grant funding body with ideas like this would be less than zero.
Why don't they go?
Well, because you look at what gets funded and it's all glossy stuff and da-da-da-da. And of course it almost never ends up in the real world, even though they say, the real world needs this. It never happens.
Well, I'm willing to throw out here we should talk about that, because we are in the real world, and that's why I've actually dumbfounded to hear that one of the bases, which is you declare about the radiance, is a blunder. The opening of the sky. I mean, that is an astonishing statement.
Well, it's a point of view. The point. I mean, you might say, it doesn't matter.
It's a statement there.
Yeah.
It's a bit like Galileo saying the Earth is round.
Sadly, it's not in that realm.
Well, maybe David is almost as much a blunder to measure daylight using photopic light.
Okay, we're really opening it out now from going purely geometrical things into non-visual effects. So, whoa there, Stephen, right? Let's just rein you in a bit there and stuff. Well, daylight's never been a hot topic for funding, anyway.
No, never.
Eleanor.
So I get the idea of that is good to have the size of the window and this idea of the connectedness for planning purpose and that. But I still have a couple of thoughts. So one is about overheating, because I don't know if it can be used as a proxy for overheating if you have higher values, results in winter at lower.
That's where you start to look at the air temperature as well. So that's just a beginning. So
temperature and the solar heat gain.
Yeah. So then you might want to put your calculation grid just inside the window frame and look at those things. So no, it's not going to be an absolute indicator of it, but I think for simple things like with the house where you see the arrangement and the sunroom and stuff, it might be a way of just in a compelling way telling people the obvious. Look, if you stick that on the south exposure, or actually the southwest like that room's going to become unbearable for 3 months of the year. And we see this in the UK. I mean, a few years ago, people selling conservatories started including air conditioning packages in there.
In the temporal map that you showed, because it was south facing, it had lower value.
I know that was for just one with an overhang and stuff. But when you looked at the whole house and all those 8 orientations, where it was the fixed arrangement, but then it was very sensitive in terms of the annual distribution, when you had it, I think, like that. I mean, I can go back to the slide if you want. Come on. Yeah. There we go. Okay, so this maybe because it's happening there in summer, and it's the whole house as well. Yeah.
Yeah. Maybe, but
yeah, it's. I mean, you're right. One thing that you might want to do, certainly in a standard, is, well, let's say, eliminate all sun altitudes below 5 degrees, say, or even 10. I mean, I'm including everything in there, so it's, showing, just for demonstration purposes, everything above horizon. So actually, no, I think the house did have a bit of the cutoff, with there. So that's one thing. Another thing you could do is actually apply some weighting factor to it. So you actually start to take account for the, you're not looking at standardized climate files, but you apply something that gives you that similar effect of much lower sun intensity. So all of those things can be factored in, but once you start from this very clean, purely geometrical basis, then you can start to gradually add whatever levels of refinement you need to it.
And the second answer is really on units, like it was mentioned before.
Right.
So the lux and lumen thing.
Yeah, I know a few people have mentioned this, because, I mean, it's totally arbitrary, the 2000 lux, but it gives you 1,000. I mean, things, once you just think of it, well, again, if you think of it just in terms of lumens, it's fine, because most of the time in daylight, we don't think of lumens. Yeah, and we just think of it as a number that connects. Yeah. Call it things. 2,000 things.
Yeah, I'll just pick up on that. Once we start thinking about how much daylight we deprive people of, then we'll be thinking about daylight in lumens. But it's only at that point.
Remember, this is you need some number. I mean, at first I thought, let's just make it simple and have 1. The sky is normalized to 1, but then you end up with such small values that seem quite unwieldy, whereas when you got this, like, each square meter 1,000, and the thing is, you kind of just edit out the unit. It's just, you get, each square meter gets 1,000 from the sky, 1,000 from the ground, then you have obstructions and so forth.
It's just especially when you make the, how did you call it? Climatization, or
climatize.
Into climate-based, maybe it becomes confusing to transfer the unit.
I don't think so. I think if people understand this, because there is a step change, but it's still, within the framework of a continuum, in that you're moving from, normalized, idealized units to real ones. You're moving from pure geometry to irradiance and all of that. Yeah, I don't see it. I mean, whilst it's okay, it's something to think about a little bit, it's much easier than trying to do a basic sun path calculation using the existing frameworks and the Waldron diagram and everything else.
Actually, I quite like, because I teach in the University of Westminster in Nottingham, environmental design and daylighting is the most important part. And it's good it could be a basis. For example, when you teach daylight and another lecture is on thermal, it's always difficult to, there's a jump between two, because then they still get confused, like how are we going to integrate, and they have to use software to check and trial and error basis. But here, from this, for example, you still can predict, saying that, well, I can see that left housing have less daylight, and also they're going to have need more heating. They're not going to introduce the sun. They may have less vitamin D, for example. So this they can use. Then they can check
to get a feel for the spatiotemporal dynamics of sunlight exposure.
Could be useful for teaching, actually, to students to understand before even they go to.
Absolutely. And the sooner you get them, the better, just like the Jesuits.
Yeah.
Yeah, so I'd like to echo that one. And that's a question.
Sorry, yeah.
Sorry, yeah, I'd like to second. Sorry, I'd like to second that because there is a massive disconnect between overheating and daylighting, and one affects the other more.
Oh, yeah, the more that daylighting message gets across, isn't this a good thing? Well, this went with the schools BSF programme. We overglazed, and you ended up with overheating.
Absolutely. And the second thing was that was the VSC component of ABDM, or whatever, ABDM. Can you produce a value of VSC that's alternative to the point value, or is it just your own specific measure of view?
Well, no, I mean it is what it is. It's there. You saw with the example with the little flat enclosed, with the balcony above and below and the sides, that you got a value which was, 25% or something like that. So you're cutting out effectively half of the direct connection of those apertures to the sky. Now, what you decide is acceptable and so forth is that that's to come down the line, I think. But in terms of actually having a basis, I think any aperture-based basis is always going to be more reliable than taking 1 point. Yeah, because we saw in all those, just taking 1 point is, it's never going to be representative.
John, you've done a lot of work on sort of what are desirable light levels for people in rooms. Are you going to be able to update that and link it to how much light is coming in with your...
Well, that's certainly something down the line, yes. I mean, because once you start off with the potential for illumination, then the next question is, well, how does that manifest itself in actual spaces?
Because one of the questions that we've asked ourselves a lot of time is where you take those measures, and the famous 300 lux on a desktop and all that sort of thing, which has always struck us as being rather unreal in terms of the ignoring tasks completely. You're assuming everybody's working at your desk. Will you be able to plug in, as it were?
Well, that's it. It's down the line. I mean, back with the New York Times study, we were calculating values at the eye then, but you're only going to do studies like that if someone's going to pay for the time, because they're quite involved.
It seems to be quite a problem, because if you're unravelling by this change what have become accepted norms out there generally in the industry, and you can't replace quickly, you say, okay, you did it that way in the past, you got a wrong answer, do it this way and you'll get a good answer. We have a lot of problems ahead of us.
Well, maybe there might be some scope for actually putting in a funding proposal to develop this as something, ultimately that would, put your fingers in your ears, replace BR209, and surfer planning, but also which dovetails with what, everything else that building designers and people who evaluate buildings do. Maybe. In which case, then you do have to come up with recommended values for these. Yeah, this is about the methodology. What your target value should be is to be decided. But I think this is a much sounder basis to start asking that question.
Yes, I'm excited about this. I'm already 10 miles further down the road.
Okay, so we're nearly there. So now, what we've got at the top there, it's a bit of a tease really, because it's the radiance image you would get if you predict the illuminance in RGB components arriving from these different scenes. Of course, it's not what you'd see, but so can you work out then? So V, which of the scenes below, 1, 2, 3, 4 or 5, produced V? 4? Any others?
3.
Okay, well, V, certainly the colour that you'd get if you mixed up red and blue. Yeah, you get that sort of there. Also, it's completely even. So I think it has to be 4.
You know the answer.
Yeah. But it still has to be 4.
Maybe you forgot.
So, what about W then? Which one's W? It's 3, isn't it? Because what's happening there is you're blocking off at the top there, you're blocking off some of that view of red sky, but you're not blocking off so much the view of the blue. So you're getting a bit of a blue tinge up there because you're effectively seeing that you're having the sky blocked, but not the ground. Whereas here you're having the ground blocked, but not the sky. So it's a little bit more reddy here and a bit more bluey there. Okay. What about Z actually?
Number 1.
Yes, yes, it's more or less the same thing with a little bit of some greenness thrown in. Okay, and so X is 2. Yeah. Well, you can actually see, can't you, a little bit of it's an alias-like effect, a little bit of a striation, which could only come from that one. Okay, so it's been indeed that is it. Yes. It's been a long session. Thank you very much for coming, and thank you very much for the questions and everything.